policy fellow at Trading for Good. He has an academic background in policy analysis, AI, cognitive science, sociology, and philosophy. And he is enthusiastic about solving policy problems with modeling and simulation under deep uncertainty. Before I give the floor to him, I want to remind you that during the talk you can submit questions and upvote each other's questions on the swap card. If you go to this event, and then to the live discussion button, and then to the questions tab, so live discussion questions. Yeah, you can submit questions and upvote it, and I'll have a Q&A afterwards of the questions people are most curious about. And yeah, give it up for Max.
Hi everybody, thanks for showing interest in this topic. I'm very excited about this topic and about the methods. I would really like to share them and would really like to see more EAs or researchers in EAs really use them. Let's get started. Model-based policy analysis under deep uncertainty. Let's break it down briefly. So I want to talk about policy analysis first. In this context, I really would like to talk about complexity first, then about modeling, then about deep uncertainty, and in the end, if there's time, as we'll have to see, just kind of like a teaser of what I can see, where we could maybe use this, and what kind of course areas would be like potentially really useful to apply these methods. All right, let's get started. All right, and basically, act on the basis of very simple individualistic rules, right? They don't have a hive mind, but there's a colony of the ants together, and those colonies perform very interesting, very intricate behaviors for nest building, for example, or collaborations, for example, such bridges, which is a really cool picture, I think. Generally, I want to say that even if you have very simple individualistic behaviors, you can actually potentially observe emergent macro behaviors that are very interesting. And it's very not clear in the first place, the initial conditions, what kind of behaviors will emerge. Because the system is very complex, potentially, very different kind of behaviors, different kind of interactions between those behaviors, kind of like an underlying system. Although this is a very simple system first. Slightly more complex system of humans, of human society, but you could also break it down there. You have people doing basic things, going to work, doing emails, whatever, and you could also potentially look at that. You could look at the interactions between those humans, and you can see, you can observe also emergent properties, emergent phenomena like culture, like society, like technology, which again feeds back and makes the interactions more complex. Yeah. So what I want to look at is like one subsystem is physical society, so just humans and how they interact, and another subsystem is technology. And I think it's very interesting to look at those, if you combine them, at socio-technical systems, and actually look at them and like really try to understand what's happening, especially with respect to policy analysis. Very interesting, right? Policymakers need to make decisions, and they need to reason through those complex systems. But it's really hard, right? Like, what kind of interventions do you need to implement that lead this kind of system into a desirable state? It's really hard to do. And we could use modeling actually to help that process. So generally, just to give some context, we're interested in the world state, and policymakers affect that world state, right, with policies. Very simple. Usually, or hopefully, policymaking is based on evidence, or we could use modeling actually to support policymaking. I think that would be really useful to do. Okay, maybe like a show of hands. How many people here are familiar with modeling in general? Have modeled? Okay, quite a lot. Now the question is, what kind of modeling? Have you heard or used or seen something like agent-based models ever? Show of hands. Okay, like half of the people are just raised their hands before. Okay, interesting. Before diving into that, the very basics. So we look at the natural system, at the real world. We want to encode that, break it down into a model, into a simplification and abstraction. To basically look at that, we usually call it a natural system and formal system. And then we want to explore that or make predictions, and then we see how what we figure out there applies to the real world again. That's basically what modeling is about in a nutshell. Okay. Okay, why modeling generally? Well, on one hand, usually we have mental models of how things work, how society works, how technology works, etc. But it can be very confusing. You have lots of contradictions. It's really hard to keep all the components in mind, right? Especially if they influence each other in very nonlinear ways. And we can use actually formal modeling to make very clear, explicit assumptions and then find contradictions to basically get rid of them. So it's very useful. Even if you don't use the actual model that comes out of this, just the process itself can be very useful already. Yeah, then one problem is that we need knowledge, and often it's incomplete. So, but the problem is, even with incomplete knowledge, it's useful to model because we need to make decisions. There's urgency. Policy making has to happen. So it's probably better to use some kind of model. I mean, ideally, if you would improve this model over time, it probably is more useful. But then it would be very useful to actually use some kind of evidence, some kind of modeling to actually support the decision making. It's better probably than just using your gut instincts for policy making. And generally, maybe you know this quote by George Box, all models are wrong, but some are useful. So, like a caveat, there are really shitty models out there. I have worked also on very shitty models myself, but you can create better models over time, and it could be still useful. But you have to be really careful, right? You cannot just say, we have this model, we use it, bam, that's like what's gonna happen. More for that later. Now to the, I think, bad kind of modeling, traditional modeling. It's basically focusing on kind of classic economic theory, usually neoclassic macroeconomic theory. You expect your actors to be rational agents. You have a very top-down view, for example, at the economy, like what GDP. So don't look at the actual actors. You just say, okay, you compute it like this. You just do it like that. It's a very top-down way of reasoning about this. Also, lots of simplification, lots of aggregation. You simplify so much to basically end up with something like elegant equations that you can easily understand and reason about, and that's usually what traditional modeling does. What I want to show you is alternatives to that. So next to traditional modeling, there are like a bunch of other models. Agent-based models, discrete event simulations, system dynamics. There are actually so many. I would actually recommend this book. I'm going to show it in the end again, like with other resources. Scott Page actually describes in this book in a really nice way a bunch of models. Every chapter he shows you a different kind of model. I think it's really useful to have this in the toolbox to know that there are alternatives. And I cannot talk about all the models obviously, but I'm going to focus on one to give you kind of a feeling of what I'm talking about. I'm going to talk about agent-based models, and like a third of the room anyway knows kind of what it is. So I promise it's getting more interesting later when I come to uncertainty, so bear with me. Okay, let's have an example. I think it's usually the easiest. COVID, pandemic. You have basically to make decisions, or we had to make decisions, still going on kind of, and models can be very useful. Some people are using those models, and there are also quite some online resources. So what I want to show you here is basically one such agent-based model. You have different communities in those boxes. You have those blue dots. Those are all agents moving around. And the red ones are basically those that are infected, right? And they are jumping sometimes from community to community or move within those communities. You kind of can run such a simulation with those agents, having very simple behaviors, and you can observe what is happening over time. And it's very interesting to actually use. If you want, by the way, to play around with that, this is not done by me, this is done by somebody else, but it's really cool. You can scan the QR code, or like later, just click in the slides, and you can just There's a lot of sliders. You can just choose the things. You can introduce quarantines. You can have social distancing rules. How many people apply? Like I comply to those social distancing rules. It's really fun to actually play around with that. Okay. Why I'm showing this to you is I think because it's a very nice example of how agent-based models, what they are about, because you have a bunch of agents and they have simple rules, and you can see kind of what happens, and especially if you use different kinds of interventions, right? And you can maybe make predictions, you can explore the system. I think it's very useful, very different to the traditional modeling. So basically what you have in the agent-based models is you have some agents, some other agents usually have heterogeneous agents, so they have different kind of rules that they follow, and those different kind of rules in that system will actually basically prompt very interesting behaviors potentially, depending on the complexity of the system. It's really hard to reason through just from just in your mental model, but if you actually make it formal, it can be very interesting. It's also bottom up, because you focus on the lowest level, you focus on the agents. You can, for example, have also like an economic kind of agent-based model, where you have people kind of working, buying goods, for example, etc., and then you observe what happens actually with the economy, with GDP, etc. Right? It's like a very different way from this classical, neoclassical economic theory, where you say, okay, this is how you compute GDP, and those are the like Largus production function, blah blah, and this is how it works, which usually it doesn't. And this is like a very different way, actually. There's a whole subfield in economics, complex economics. It's actually pretty cool. Yeah. It's also very interesting in traditional modeling. You focus basically, like in economic theory especially, you focus really on equilibria. You assume that the system is kind of almost static, which in reality doesn't seem to be the case. And what you can do with those kind of models actually really simulate potentially bubbles, financial bubbles, crises, for example, which you cannot do with traditional models. So it's pretty interesting. You can observe or explore black swans. You have fat tail distributions that you can explore. It's really interesting. It opens up new opportunities for researchers to actually look at those systems in a different way that traditional modeling often doesn't offer. And I think I mentioned this kind of already. Basically, you have this action feedback loop where you can have reinforcements and you have like emergent behaviors that you cannot initially predict. It's a very different approach. Okay, so much for the crash course on modeling. Now to the main part, deep uncertainty. First, let's talk about real-world political decision making. Usually knowledge is incomplete, it's uncertain, it's contested by the stakeholders. People don't agree about how the real world works. And that's really a problem. In a stakeholder meeting, you have different agendas, you have different values. It's really hard to find like a consensus, right? For example, formulate a problem and agree on the goals. And there's no correct way of framing a problem. There are always like a bunch of different ways, there are different problem perceptions. It's really hard to actually think this really through and have something properly done. And you have ways of formulating the problem, and you have problem-solving process itself, and they are quite intertwined, affect each other actually, which is also quite ignored in a lot of contexts usually. And this makes, well, policy analysis or policy making very hard actually. So let's put it in some context. So we have here on the x-axis knowledge, and at different degrees basically. Certainty, risk, you know the probabilities, deep uncertainty, which I'll explain in the next slides, and unknown unknowns. Basically it gets more difficult the further you go to the right. On the y-axis we have values. Single measure of goodness, you just have this one thing you care about. I don't know, in economic theory care about the consumption in a state or in the world, for example. Like very simple. You have multi-attribute utility, where you, for example, you have a function, you have different goods, and you basically just put them in, and you output just the utility value. And that's basically you also quite aggregate those things. And you have, on top here, value diversity, meaning you have just independent metrics, independent quantities that you care about. Could be consumption, it could be quality, it could be justice, freedom, safety, whatever. Depending on your system, depending on what you care about, you can have that kind of stuff. Okay, so a lot of the decision analysis techniques actually focusing on this area here, which is a problem. It's like, it makes it easy because you know the probabilities, or you even have like something like a deterministic system. It's easy to do. You have not many metrics that you care about. You can do things, and that's good if we actually live in a world where the real political decision making would actually be here. But I think it's actually rather there, and those normal techniques do not actually work for those because we have just completely different assumptions, like with the values and the knowledge specifically. So how can we approach to solve this area, to actually do something about that? Okay, that's the most texty slide I will have, so sorry for that, but it will be over soon. I'm going to explain. Okay, deep uncertainty exists when parties to a decision do not know or cannot agree on 3 points. One is the system model that relates actually to consequences. So how do you map inputs, for example, actions, to actually consequences? So you either do not know, or maybe different stakeholders you cannot agree on that. Or you do not actually know, like for those inputs, what kind of probability distributions do you have? So you actually do not, you know about the factors maybe that you are uncertain about, but you do not know what the probabilities are actually, right? And the third one is also in the stakeholder kind of setup, you don't know actually which consequences or which metrics you actually care about, or what the weights actually are between those metrics. Okay, so that's kind of deep uncertainty. So you know the factors that you care about, so you know the factors that you think are uncertain, but you actually do not know usually the probabilities. I think that's like one of the key things, especially. Well, uncertainties are literally everywhere. So what do we do with that? There's a field called decision making on deep uncertainty. It's really cool, and it has 3 basic pillars. So one is decision aiding. So you do not make really predictions with your models. You do not want to dictate policies. You're not just going to run a model, say, hey, the policymaker, here's the optimal policy, go with that, it's going to solve all your problems. That's not the point. You just want to basically help, aid the decision maker, and you want to have an adaptive kind of framework where you want to say, okay, we also with the unknown unknowns, I'm going to come back to this later. You want to be able to adjust in the future when things happen and act accordingly. And I think the most important aspect is this exploratory thinking, where you don't actually want to make any predictions with this kind of framework. Not at all. You want to explore the system, and you want to explore what you can do to find especially very vulnerable scenarios in the future, and kind of find robust solutions to that. It's kind of very in line with S-risks, where you really want to avoid those really troublesome situations by having policies that still perform okay or well, even in very bad situations. And that's like one of the key messages. So you don't want to maximize your overall performance, hoping for good scenarios. You just basically want to minimize regrets. You want to really find robust solutions that perform still okay, even in very bleak futures. Okay, so the last point of the exploratory one, I just want to make it really clear that there is a difference. So you have predictive modeling, in which I think you usually pretend you have a magic crystal ball of your model, and you can look into the future. So you predict and act. That's kind of the way how it goes there. With the exploratory way, it's more explore and adapt. Okay, it's very different. I'm gonna make an example like on further slides what this really means. But now I wanna still make one point. How do the predictive modelers deal with uncertainty? But usually they're kind of surprised that they exist. And how to deal with that? Basically, you have the model with uncertainties, and you're just like, okay, just run it 10 times, average it, and that's like how it goes. Yeah, maybe not the best solution. I I think the explorative modeling framework has a better approach to that. But before I go into an example of that, I would like to show you how information can be structured with the model, which is usually really useful to think about that. So the XLRM framework is developed by the RAND Corporation actually, which is really useful to just structure this information. So you have the relations, which is basically your model, for example, your agent-based model or any kind of model that kind of maps inputs to outputs. One of the inputs is L, policy levers. Basically, you can say, what are your potential actions? You can have different ones, you can have different dimensions, you can have 1, 2, 3, whatever, how many levers you want to use. And for the jargon, or for basically how we are usually referring to this is a policy. So if you consider basically all the dimensions of the different kind of levers, they span a space, and a point in that space is a policy, right? It's a potential combination of different levers. And we wanted to usually try to find an optimal policy in it. So like one of those points, a combination of those levers. Then there is X, like XLRM, exogenous uncertainties, so things you can't control but actually happens and affect your system. It can be very simple parametric uncertainty, it can be structural uncertainty where you have actually completely different functions and where you're uncertain how this works depending just on the system you want to look at. And also there, basically all the different kind of, you can have different variables basically for uncertainties. Again, different dimensions. You can have 5, 10, however many you want. And again, the uncertainties span a space, and that space is uncertainty space, and a point in that space is a scenario. Okay? So basically, it will happen in the future. You don't know what it will be. You don't have influence on that, and that's going to be a scenario. Okay. So you map the relations X and L into M, performance metrics you care about, and it can be one metric, it can be also several metrics. Actually, this whole decision-making legal uncertainty framework deals really well with multiple objectives that you can have. But I'm going to show this in a moment. So what you actually want to do in that is, you can just run the model, right? You just give your policy levels and your uncertainties, so that's some kind of evaluation to the model, you run it once, you get some outputs of the metrics. Okay, but that's kind of the predictive way of doing things. The exploratory way of things is usually that you actually want to optimize the performance metrics, and you want to find the policies that actually optimize them. So you embed this whole framework, your entire model, into an optimization setup, and then find the optimal policies that will lead to the optimal performance metrics. Given that we actually have multiple objectives, multiple metrics that we want to optimize at the same time, it's a bit hard. So the normal notion of optimality doesn't really work, and we use Pareto optimality. I have extra slides in the end that won't show you. If you have questions, I can still show them, but I think it would take a bit too long now. But there is a way of how to find optimal policies, even if you have several objectives. Okay, so much for that. Let's have a look how this could work. There are different ways of how to go through such a process of decision-dependent uncertainty. I'm going to show you one way. So basically, first we start with specifying a model, you see parameters, hyperparameters, etc. The second step is actually you pick specific scenarios that you care about. You usually try to find in that uncertainty space, you try to find a subspace of that where your metrics perform extremely badly. And that's basically the space you want to look at and explore. And then you want to find scenarios actually in there that represent that space in the best way. And that's your basis with which you then work on to find out optimal policies in a moment. There's a little AI symbol because usually you use AI, like usually you use supervised or unsupervised learning to find those kind of things. Like that's like there's a bunch of literature behind that actually. But okay, so basically you start with your reference scenarios that you work on. On the basis of those reference scenarios, you want to find policies that perform optimal on that. And for that you also use AI usually. And They use usually evolutionary algorithms. That's what you do usually. Actually, multi-objective evolutionary algorithms. That's like I also have a book recommendation in the end for that. But you basically try to find more optimal policies given the random scenarios that you defined before. And for that, you get basically your Pareto optimal policies out of this, your set of optimal policies. Now, those optimal policies are only optimal for the reference scenarios though. So that's a problem. So you actually reevaluate those policies under deep uncertainty. Just means basically sample a shitload of scenarios, like thousands, 10,000s of scenarios, and just run your policies that you found in the step before on those scenarios, and then you see how they perform. You look at the outcomes. Okay, there's like only one step more after that, and it's like almost done. Then you basically have more data. You see basically under a lot of different scenarios how your policies perform, and then you want to discover more scenarios. Like in that subspace, you want to find again where do those optimal policies perform badly. And if you find that subspace, you can constrain that subspace space again, and then you basically start over and do it a few times, and then you end up with a lot of data that you can use for something we call trade-off analysis. Okay, I know it's a lot, but basically find a bunch of scenarios first. On those scenarios you optimize, find your Pareto optimal policies, you get a bunch of outcomes out, and then you try to do this basically again, for tinier space, and in the end you basically look at the trade-offs. So how does it look like, usually? That's an example of a paper that focuses actually on climate change. It's pretty nice. This is a parallel axis plot. So basically you have different kind of axes here. Each of these axes represents an objective that you care about. Basically higher values there, like more up, basically mean that they are more desirable. And a line that you can see here, for example, let's say line A, the black one, just basically shows you one simulation line, of one optimal policy applied to like a specific scenario. You do this a bunch of times, you see actually a lot of lines, and I'll show that the resolution is high enough. But the A line basically is, for example, 1. And you can see that actually low utility comes usually with a desirable warming above 2 degrees Celsius, like with the second objective. So you can see if you actually want to have something that's actually good on the second objective, you have trade-off with the first objective, for example. And so you can see, you can identify those trade-offs. And the nice thing is actually that you can go to your stakeholder with that and say, hey, you care about, for example, those 4 objectives, but you can't have it all, at least not at once. So you have to so the policymaker, the stakeholder, has to make a decision what to do, what to choose. Those are all optimal policies in different scenarios, but they have still to choose now which of these policies they go for. But that's up to them. That's not up to the modeler. In the normal way of modeling, you often don't have this. You have usually only one axis. You have one objective. You actually aggregate everything before. Maybe you applied some weights to those objectives, but you do this basically a priori. But here you do it a posteriori, right? You actually offer this trade-off and then can show this to the stakeholders. And with them you can make decisions what policies they actually would prefer. Another thing is, what you often have here is this kind of spans, say those were 3 variables, each span an uncertainty space. And you can see here that a lot of data you have, and those red dots here represent basically the scenarios where it performs extremely badly. And you can see that you can look at this and you can basically say, okay, we actually care only then about for example, those here, and there we want to zoom in. That's like how it usually works. And then you look only at that space and you continue to iterate, for example, and so on. Or you actually talk with your stakeholder about that you actually want to avoid those areas. And for the adaptive thing, it's another fancy plot. Don't go too much in detail. But basically, it's about adaptive planning. You say, for example, to the stakeholders, hey, over time, you will get more data, right? You will I mean, time passes by, things happen, and maybe you are first in that area, which is okay, and then slowly you maybe happen to actually end up in that scenario here where it's actually quite bad. And then you want to maybe adapt your strategy, you want to adapt your policies. And this kind of subway map shows you that a little bit. For example, each of those lines is basically a policy, and you can see here, those are like tipping points. If you reach a specific point where it's going into one of those areas, for example, you should basically switch to a different one, for example to the green one here, because it performs better. So you have this adaptive planning way of thinking also included in that kind of decision making under deep uncertainty framework, which is pretty neat. Yeah. Just want to show the fancy plots, and you can use them. It's basically the purpose of the slides. Okay, so that's nice. We can use that framework. What are the drawbacks? Well, generally for modeling, it's really hard to actually put like a natural system into a formal system. You have to make a lot of decisions. Even though if you include a lot of uncertainties as well, you still have to make a lot of decisions. It can be very hard, and validation can be also really hard, especially in an agent-based model. That's kind of the downside. Yeah, and if you then try to go with all your plots to the stakeholder, it might be also hard to convince them, hey, this is how it works, and they don't have such a attention span usually. Usually what they want to see is like, okay, give me a prediction, give me like one policy, and it best fits my agenda anyway. So that can be quite hard. And the third point is DMDU, decision making under deep uncertainty. Well, it requires a lot of compute. Depending on the complexity of your model, you look at thousands of years of runtime on a single core. So it kind of competes with normal AI deep learning training, I think, like to some degree. But it depends on your model that you're actually looking at, or in your system, and the complexity of that system. Yeah. So there are some drawbacks. I think they can be overcome. I mean, the alternative is just pretending you have a magic crystal ball and you can predict the future. So I think gotta deal with that.
Short question to the last slide. What was DMDU standing for?
Yeah, this DMDU, sorry, is decision making under deep uncertainty. That's kind of the framework. Yeah.
Thanks.
Yeah. It's a good question though. Okay, application areas. Maybe very short because we don't have much time. So basically, I think it can be really useful in biosecurity if you look at COVID situations, pandemic preparedness, considering different uncertainties, considering different kind of subsystems that also not only focus on disease itself, but actually also on economic impact, for example. I think it can be really useful. You can look at economics, especially complexity economics. You could look at governance and improving institutional decision making, which I actually really try to focus on. This could be really interesting. Climate change, which is also done quite a bit actually, which I also did recently. Nuclear weapons, AI, and actually long-termism. I'm not an expert on all of these fields, but actually there are quite some application fields. There's actually also a forum post by Rory Gregg who actually talks about this as well. Pretty interesting. I'm gonna link it too on the slides. You can have a look. But yeah, okay. Takeaway. I think that's important. All models are wrong, but some are useful. So we can really still make use of some of the models. Basically, if you want a model, you can either just ignore the uncertainties, just pretend you know what's happening, make assumptions, or you can embrace uncertainties and just use an approach where you really consider uncertainties in a systematic way, like with the decision-making and the deep uncertainty framework. And I think this is also really important. You don't want to maximize expected future performance because you don't know what the scenarios are. You just want to minimize plausible future regret. You just want to find robust solutions that work also in very bleak future scenarios. And almost done, 20 out of 30. If you scan the QR code, you get access to the slides, and then everything is actually kind of linked. What I would recommend, what I mentioned already, the model thinker for a bunch of different kind of models. Very useful, I think, very entertaining. If you want to dive deeper into agent-based models, one of my former professors, co-wrote this book. It's pretty neat, pretty basic. You can get into it. If you really want to go into decision making and uncertainty, and that's the book out of 2 years ago, it goes into very different methods that are used in this field. If you care about how to actually use those evolutionary algorithms to find those optimal policies, and if you care about Pareto fronts and that kind of stuff, then dive into that book. It's like 800 pages long and it's super mathy, but I had fun reading it. So if you're into it, go nuts. Then the forum post I already mentioned by Roy Gregg is also linked. If you just have the slides, you can just click on it to actually get there. It's pretty neat. And there's actually also like a entire society that focuses on those methods and develops them. There's also a link to the website, and you find a lot of research there as well. And this concludes my talk. I think we go to questions here.
Yes.
Raised the hand already.
Oh yeah, thanks a lot for your talk, Max. This sparked some interesting questions. I'm not sure how well Swapcard is working. I couldn't upload answers, for example. But we'll first go through the questions on Swapcard, and if you have remaining ones, we can just use raise hands.
Could you go back to the previous slide?
Yes. So for the QR code or?
Yeah.
Okay.
Thank you.
Okay, then I'll skip the question that asks to go to slide 21. One question is, with which tools do you create such models? How much time does it take and what amount of data or information do you need?
Okay, wait. So the first, can you repeat the last one?
What amount of data or information do you need?
Okay. So the first question, what kind of tools do you use? You basically have ready-to-go libraries. A lot of people are using Python. There are also different kind of frameworks like NetLogo, which is like an old thing which I wouldn't look at. But also Java or whatever. But I think Python has a bunch of different libraries. For example, Mesa, and like a few more popping up. So you basically can use those. They have like those APIs. You can follow the tutorials, and you can actually just dive deep into them. And for the data, I guess it depends on the model you're working with, or the system that you want, or the problem that you want to actually model, and the stakeholders. I mean, you could, for example, consider, for example, let's say COVID, for example. You probably need kind of your populations, you need kind of data on how quickly the disease spreads, what kind of, there's a bunch of data. It really depends just on the specific problem you're looking at. You can also deal with it with less data or with more data. More data usually because it fits. You can actually validate the model in a better way. Answers the question, I hope.
We have a bit of a general question, but many people have covered it. How do you deal with the problem that society is so complex that it is a chaotic system where small changes in the initial conditions could change the outcome a lot?
Yeah, that's where I think those, for example, agent-based models come in really nicely, because you can actually look at the interactions between people, for example, and you can kind of abstract, and you can kind of say, okay, there's some face validity a little bit. You can look at, okay, this is how people usually behave, and the complexity kind of only emerges then when you actually have all those people interacting and affecting each other. You have those feedback loops, and they just occur. You do not have to program them in explicitly. They just happen. That's the beauty of the approach.
And then we'll have to move to slide 21. 2 questions for slide 21. Curious what's on there, but
the big one. Yeah.
the first question was, how do you avoid overfitting on the chosen scenario space? Presumably, you can't think of all uncertainties, i.e. there are unknown unknowns.
Yeah, so that's why the overfitting basically only happens if you pick specific scenarios in the scenario selection process, and that's very problematic, sure, and that's why you have this whole branch basically of this niche of this kind of science here, that usually go into scenario selection, scenario discovery, and really think it through what kind of scenarios you're looking at. I mean, you really need to look at an uncertainty space, and then you want to look at this really vulnerable part, and you want to find points in there that kind of represent this space in the best way, that are maximally diverse from each other, that you kind of cover everything. But of course, it's really hard. And the more scenarios you actually would use, and more reference scenarios, the better it would be. But of course, it's computationally more expensive, and it's kind of a trade-off usually between those. And for the uncertainties that you kind of miss potentially, because you just not include them into your model, yeah, of course it's a problem, right? But you have to make also the decisions. I probably would opt for more uncertainties. It doesn't increase necessarily the compute requirements. That actually usually happens mostly with if you include more metrics and more policy levels. That makes it way more computationally expensive. But I think you could just usually throw a bunch of uncertainties into this as well. But yeah, you have to identify them and actually put them in, and also decide kind of on the ranges, like what kind of range are you looking at then between this, and then it will sample in that space, basically, in that subspace. Hope that answers the question. It's really weird to not actually talk to the specific person that asked the question.
Now we have another question about the same slide. Why don't we directly do policy discovery on the whole scenario set instead of only optimizing on one scenario and then iterating?
Yeah. Compute. I mean, you basically need to. So how this works with like different scenarios? You have these reference scenarios there, and you run usually like a many objective evolutionary algorithm, and you try to that goes through different stages, right? Like it creates different kind of children, it mutates them, it tries to find different like generations, and basically finds a better policy. But it's always on this one scenario. If you now consider like a huge scenario space of different dimensions, then you have continuous variables, right? Like floats basically. You have infinitely many scenarios that you would consider, and you can't run like an infinite amount of scenarios. So you have to choose. That's why you have to select them in some way.
Yeah, that's my question. So I mean, so a quick small counter question would be, I mean, sure, okay, everything is very, very difficult, but again, one alternative would be to say, okay, we look at all these sets of 3, 5, or 10 or so, which would be not that much more computationally difficult than just using one. So this was my main thing that I didn't understand.
Oh yeah.
I would feel with maybe 10 or so, I would feel more, because then you can also avoid making you need less iterations and you have less overfitting. So this is what I didn't.
Yeah, definitely. I think it's definitely a problem to only use one reference scenario in the situation. That's why it's usually used several ones. And if you have just more time, more compute, you can do 4, 10, or whatever. Like it's definitely like a possibility, and definitely avoids overfitting then for this one scenario. But when you go through this anyway here, you actually reevaluate those policies, and if it was overfitting, you still get a lot of scenarios then, because so you sample a lot of scenarios, and then you realize how many policies are performing really badly on those. So you actually have to reiterate, find another reference scenario, and then you will have to do this more. But yeah, if you directly start with more reference scenarios, you're probably gonna have to do less iterations, fewer iterations, and it's a bit fun for that.
And then probably the second to last question. In EA, expected value theory is quite prominent, but often we have deep uncertainty. So often robust decisions are outperforming expected value decisions based on assumptions. What do you think about this, and do you have any easy applicable methods to make more robust decisions?
I'm not sure I've got a question. So that we usually use expected utility theory, but then we use robust decision making as well. Can you
Okay, so the question for me. So it's basically you have different approaches to make decisions. One is expected value, and the other one is robust decision making. Right? So, and I've seen a paper where this had actually been tested, and when we have deep uncertainty, where our uncertainty about probabilities is sufficiently high, I think higher than 5%, then the robust decision-making approaches were outperforming the expected value approach in the outcome. And I think often we have this deep uncertainty where we don't know the probabilities. But we still, in effective altruism, often use expected value, even if we don't know what we don't know. So we just make assumptions and then make this expected value decision. But thinking about it, we actually might want to do more of this robust decision making. Now, I'm not that deep into decision making. I don't know perfectly how this works. So my question would be, how can we make more robust decisions in a kind of easy, applicable way? Because usually it's kind of a complex thing, isn't it?
I would use that. So, I mean, you basically really need the modeling first. I think it's really useful, and then you can really use this framework to actually really, find those robust solutions. And I think, for me at least, let's say like 2-3 years ago, there was the case that I was also just like thinking about maximizing utility, because that's, I think, the only tool that I knew about. So yeah, that's what I went for. Also just usually with one objective, because like how do you optimize several objectives? But I think those tools actually offer solutions to that problem. You can optimize several solutions at several objectives at the same time, and you can find really robust policies and robust solutions. Yeah. I think that's one way how you could actually do that. Yeah.
Okay.
Just have to know about that and
Okay.
use it.
Thanks.
One more question. What would you say to a person who argues that your modeling only gives the illusion of understanding and control and may actually harm decision making? E.g., intuitive decisions are better than our explicitly modeled decisions.
I would like to see a study on that, but I doubt it. I think if you really look at very complex socio-technical systems, it's really hard just to reason through and really consider all the second order and third order effects of those tiny interactions of those different agents, for example, that might occur. So I think often it's really useful to at least supplement the current decision-making process with modeling. But yeah, obviously all models are wrong, some are useful. Just take it with a grain of salt. You should not fall prey to, okay, this is my model. But also that's what I think is really useful. Like, it's not a magic crystal ball, you know? This is not territory, right? So you have to still be aware it's just a tool, it's just an abstraction. But I think you can still use this kind of framework and just explore the system instead of making predictions, and therefore find interesting insights, find tipping points in that system that you can try to avoid in your policy-making process there.
Can I ask a question?
Only if it's very brief.
No, not
Then maybe afterwards you can connect. Maybe the perfect last question, very brief. Are there any projects or open questions to get involved with?
Okay, there's one project I cannot talk about. And there is, basically, I feel like, except for this one project that's starting right now, I feel like this is not done much, especially in the EO community. There are like a few researchers around the world, usually some are in the RAND Corporation, some are in the Netherlands, for example, and some in Italy, but there are not many that actually use those kind of techniques, and especially not on EA cost areas. Right? It's usually on water risk management systems, climate change, it's used a bit, but not for those cost areas I showed just before. And I think it would be really valuable actually if people would do that. And I really want to actually start an own project working on this and using those techniques, and I'm actually looking for collaborators to actually work on that. So yeah, it's really well.
Okay, thank you everyone. At stake.